Greetings, everyone. My name is João Luiz Pereira. I'm a PhD student at Federal University of Itajubá, located in Brazil, in the state of Minas Gerais. First, I would like to thank the organizers of COBEM 2021 for their commitment and dedication to promote this important event in light of the health situation we are experiencing. Our work, whose name is a new multi-objective optimization algorithm inspired by Lichtenberg figures applied to Isogrid structures, brings the first meta-heuristic registered in Brazil for the first time in Congress. The algorithm is the result of research developed in the Computational Mechanics and Optimization Group, or GEMEC in Portuguese. This presentation is divided into 4 parts. In the first one, I will talk about meta-heuristics and their importance in engineering. Then, I will explain about the Multi-objective Lichtenberg Algorithm, or MOLA. So, I will talk about the Isogrid structures and how the optimization of this work was done. Finally, the conclusion. With the advance of computing and data science, more robust and efficient algorithms have shown more capacity to find optimal solutions compared to classic optimization methods. The meta-heuristics are an exponent of artificial intelligence in optimization problems and are currently the most used tools in complex engineering problems. These types of algorithms are better able to deal with nonlinear, multimodal, discontinuous, and with a large number of input variables and objective functions in the same problem. The most used are SPIA, NSGA2, MOEA-D, and MOPSO. According to the no-free-lunch theorem, none of all meta-heuristics can be excellent at solving any type of problem. A certain algorithm may be better for a specific application. Still, there is a constant battle in science for algorithms that can deliver better answers at a lower computational cost. Nature is a valuable source of inspiration for new algorithms. These reasons led to the authors to create a new meta-heuristic in its single objective version in 2020 and the multi-objective version in 2021, both published in expert systems with applications. The Lichtenberg algorithm is inspired by the physical phenomenon of lightning, which generates luminous figures with turtle aspects receiving the name of Lichtenberg figures. The formation of fractals in these figures is very common. For more details about the algorithms, see these papers. How it works. The algorithm is fully numerical and does not require the use of theoretical equations for its operation, since the lightning strike modeling uses the theory of diffusion limited aggregation, DLA. In this theory, a matrix of zeros is created with a central unitary element. Then, stochastically a cluster grows and a Lichtenberg figure is created. See the first figure. The Lichtenberg figure is fed at each iteration with different sizes and rotations, controlling the population distribution in the search space. In this way, the algorithm is the first to have optimization routines based on population and trajectory at the same time. To improve the algorithm's exploitation capability, or precision, a second Lichtenberg figure with the same center point and rotation, but smaller size, can be created. See the central figure. Each point in the search space evaluated in the objective functions of the problem generates a point in the objective space. These points are compared using the Pareto dominance relationship, and the dominant solutions are excluded. Any of the decision vectors of the solutions that remain, that is, that make up the Pareto front, are candidates for triggering the Lichtenberg figure for the next iteration. See the last figure. The model has 7 parameters. The first 3 are used in DLA, being RC, the creation radius, and P, the number of particles that can be in the cluster, and the stickiness coefficient S, which controls the density of the cluster. Top is the number of points in the cluster to be evaluated in the objective functions at each iteration, black dots in the central figure. Half is the rate that reproduces a Lichtenberg figure at a half rate lower than the main one, forcing half of the pop to stay in it. The red one in the central figure. To improve exploitation. M is a parameter that controls whether the optimizer creates a Lichtenberg figure. If 1, use the same Lichtenberg figure in every iteration. If 2, creates one at each iteration. If 0, it lowers our optimized Lichtenberg figure with optimal RC, MP, and S values. Both will then be applied to the optimization of Isogrid structures. Isogrid structures are those that are hollow and formed by a set of triangles. The analytical determination of the behavior of these structures is very complex and has only been advanced with finite element software. This work focuses on applying MOLA to an Isogrid tube made in composite. In possession of the program in ANSYS APDL and using design of experiments, the meta-models of mass and Tsai-Wu failure criterion were obtained. Both are conflicting and must be minimized. The indexes of the meta-models are those in the table, and the three design variables are those shown in the figure, being the angle of helical ribs with respect to the axial axis of the structure phi, width of circular delta c, and the helical delta 8 cross pieces. The upper and the lower bounds of the search space are represented in the optimization problem. In order to compare, one of the most used algorithms, the NSGA2, will also be applied. Here we have the Pareto fronts found by the two algorithms. It's possible to note that even with the same population and the number of iterations, MOLA managed to find a Pareto front with more solutions, more continuous, and slightly more convergence. Therefore, it will be chosen for discussion of solutions. Several decision-making techniques can be used. Here, two will be chosen: the Pareto front point closest to the ideal, and the TOPSIES point, which is, at the same time, close to the ideal and the farthest from the worst, also called nudge point. Both are in table. With these variables, a simulation can be done in SAPDL to verify if they are viable and have the correct answers from the model. We then have the following models and the results. A difference can be observed between the meta-model and the finite element software response, probably generated by the polynomial approximation for this complex problem. However, with the Tsai-Wu below 1, there is no danger of failure. The main objective of this work is to bring the first multi-objective meta-heuristic registered in Brazil and the first hybrid in the world, in the best knowledge of the authors, and show that it can be successfully applied to engineering problems. Still, it has results as good or ever better than one of the most used algorithms in the world, the NSGA2. Optimal design variables were found for Isogrid tubes that met the criteria and were validated in a new finite element software simulation. Thank you very much for watching this presentation. I hope you enjoyed it and I am available for any questions. I would like to apologize if the English got a little confused.